Hello there, Mr. Sutton bringing you this lesson on separable differential equations. In this one, we're going to solve differential equations in which the variables can be separated. We're going to start this lesson off with a different kind of differential equation. Pause the video and see if you can spot the difference in this one. So this is a new situation where we have an output variable, which happens to be a y in this case, in our differential equation. Now this would be an issue even if it were just y by itself, because you'd be trying to integrate with respect to x, but you'd have a y inside your integrand, which we know from substitution is a big no-no having that kind of mismatch. But we've also got another variable in there, so this is just a mess. How do we resolve this situation? So for a lot of these situations, we can use something called separation. We're going to separate the variables and the differentials so that the y is with the dy and the dx is on the other side. I'm not going to say the dx is with the x because you're going to see some equations where there isn't even an x. But the important thing is dx has to move over so it's not with the y's. So I'm going to do this in two steps. First, I'm going to divide both sides by y to get it over to the left. So I'll have dy over y, or 1 over y, dy over dx equals 2x. And then I'm going to move the dx over here. Now, you can actually treat this kind of like a fraction. This dx is sort of a denominator that you can multiply by both sides. Because remember, this dx is just a tiny, tiny, tiny little differential, a little change in x. So multiplying it over there, I've got now 2x dx on the other side. So now what? At this point, we're going to integrate both sides. So on the left side, this is going to be ln absolute value of y, not too nasty there. And on the right side, this bumps up to a 2 for the power. Dividing by that, we have x squared. Now you might be wondering, what about the plus c? It turns out you could theoretically put a plus c on both sides, but then you could just move it all over to one side and have just some other random constant. So by convention, we're going to put the plus c on the side that does not have y on it. So on the right side in this case. And there's lots of good reasons for doing that. The best reason, really, is that you're going to have to isolate this y by the end of this problem anyway, so why have more clutter over here than you really need? All right, now what? Well, you might remember from our last diffie-q lesson that we have to figure out what c actually equals if they've given us an initial condition. So we're going to use our initial condition to find that c value. So we're going to plug in -1 for y, and over here we're going to plug in 0 for x. And 0 squared is 0, ln of 1 is just 0, so we have c equals 0, which isn't a horrible c value. At this point, just like before, we are going to plug in our c value, and we'll use our initial condition to clear up any absolute value plus or minus kind of ambiguities. So you'll see the absolute value thing we have to clear up on this one. We have an absolute value of y here that we don't want to keep around. So looking at my initial condition, I see that I have an initial y value of -1. So if y is -1, that means that this y in here is going to be negative, which means we have to force it to be positive by negating it. So I'm going to rewrite this ln as ln of parentheses -y. And then I'll still have my x squared on the other side, plus an invisible 0 that I'm not going to bother writing. Okay, do you remember what we have to do at this point? Probably not, because in this situation, I mean, after this step here, we've always kind of been done. But because you had to do some stuff with y on these problems where you didn't before, now we have to consciously isolate y. So here, we can raise e to both sides to get rid of this ln. That'll be -y equals e to the x squared. And then multiplying or dividing by -1, we have y equals -e to the x squared. Here's another example for us to try out. Pause the video and give this one a shot. Now first, before you do anything, do we need separation on this one? We do. How do we know that? Because there is a y in our differential equation. It doesn't matter whether or not there's another variable. If you have an output variable in your differential equation, we need separation. So we can start by multiplying y to the left side. That's going to be y dy on the left. And we'll multiply dx to be over on the right side. So that'll be 2 dx. Next, antiderivatives. Antiderivative of y, this is going to be 1/2 y squared. And over on the right side, this is going to be 2x plus c. Plugging in our initial condition now, we have 1/2 radical 3 squared on the left. On the right, 2 times 1 plus c. So radical 3 squared is just 3. This is just 3 halves on the left. On the right, we have 2 plus c. Subtracting 2 from 3 halves is going to give us negative 1 half. So there's our c value. Now to plug it all back in. So here was our general solution. Now we have a negative 1 half for the c value. And there was nothing to really resolve before plugging that in. But we do have to now isolate y. So first step, I'm going to multiply everything by 2. So that'll be y squared on the left equals 4x minus 1 on the right side. And at this point, to get y by itself, we need to take a square root. Now you might remember, when you square root an equation, we get a plus and a minus. So do we have to write y equals plus or minus radical 4x minus 1? It turns out we can't. This is the same kind of ambiguity that absolute value is giving us. We're essentially giving people 2 different particular solutions instead of just 1. So to resolve this situation, we again look at the initial condition. In our initial condition, we have a y value of radical 3. Well, if radical 3 is our y value, that means that in general, y has to be greater than 0, positive. So choosing between these 2 different things, we have to choose the positive square root, not the negative. So we'll write then y equals positive square root of 4x minus 1. We're going to do one more example, and this one has a few curveballs in it. One of them you might have noticed is we're not doing the normal variables x and y anymore. Now we've got these h's and t's. So first off, which one is the input and which one's the output? It turns out here that t is the input and h is the output, which we can tell because t is on the bottom and h is on top. Now, do we need separation of variables here? Well, noticing that we have this h, this output variable over here, we definitely need some kind of separation to make this work. So how can we do it? One of the keys to this is that you're not allowed to separate by adding or subtracting. When you move things to be over with dh, you need to have things multiplied by dh, not added or subtracted to it. And dividing is the same as multiplying, it's just multiplying by the reciprocal. So how can we do this? Well, you might have noticed on this one that we have a t to the negative 1 factor in both of these terms. So sometimes you may need to factor before you can actually separate your variables. If we do that on the right side, we can write this as, and I'm just going to factor everything here, 3t to the negative 1, parentheses, h minus 2. And now we have 2 different factors. We've got h's completely inside one factor with no t's hanging around. That's important. And we have this other factor. So doing a little separation now, we'll divide both sides by h minus 2, that whole thing, to get it under the dh. And then the dt will come up to be here with the 3t to the negative 1, which we could call 3 over t if we wanted to at this point. It doesn't really matter one way or another. All right, pause the video and see if you can finish this one off. Okay, so we need antiderivatives. We're going to use ln in both of these cases. This is a 1 over something kind of situation. So on the left, we've got ln absolute value of h minus 2. On the right, we have 3 ln absolute value of t plus c. And now plugging in our initial condition, we've got on the left ln of h minus 5, or actually 5 minus 2, I should say. And then on the right side, we have 3 ln of negative 3 plus c. So this is really ln of 3 on the left. On the right, this is 3 times ln of 3. 1 ln of 3 minus 3 ln of 3 gives us negative 2 ln of 3 for our c value. Okay, time to plug things back in. But you might have noticed we have some absolute values here that we have to take care of. Let's figure out the h first. So we have an initial value for h of 5. That means that 5 minus 2, or h minus 2 in general, is going to come out positive. So I can drop the absolute value and just replace it with a normal parentheses, like so. So ln parentheses h minus 2. Now we have to take care of this ln absolute value of t. Our initial t value is negative 3, which means t in general is negative for this problem. So I'm going to have to replace this with 3 ln parentheses negative t. And then don't forget to actually put that plus c value on there, so minus 2 ln of 3. And at this point, all we have to do is isolate h. So to make my life a little bit easier, I'm going to merge all the logs on the right side, because if I have a log on the left and a log on the right, then I can just cancel the logs, but I can't yet. Let's merge these. So I'm going to first pop in these coefficients as exponents. So this is going to be negative t to the 3rd power, and I've got just ln of h minus 2 on the left still. That's not changing just yet. So we have negative t to the third power. And then I'm going to be dividing that by, because I'm subtracting the log, this is going to be, let's see, this pops in as an exponent, so this is going to be 9 in the denominator there, all inside one big ln. Now I can just cancel out the logs, and then I can just add 2 to the other side. So I've got h equals negative t cubed over 9 plus 2. So it's been fun, but now it's time for us to go our separate ways. Until next time, Mr. Sutton signing off.